Hello everybody, and in this video we're going to continue talking about thermal radiation. But if we're going to talk about thermal radiation, we better define what temperature is. So I was introducing this in the last video where I took you into my kitchen and we were looking at an object as it heats up. We were seeing that as something heats up, it gives off more and more light. We also were getting to see that objects that are room temperature or a little bit warmer, like you and I, give off lots of infrared light. So you can see with this camera right now that I am glowing pretty brightly in the infrared. I also have these three juggling balls sitting here. One of these I was holding in my hand prior to starting this video. Let's see if we can figure out which one. All right, that one looks like it's pretty cold. Middle one's pretty cold. Oh wait, that one is warm. Okay, so now I can use the thermal light that this ball is still pretty warm from when I was just holding it in my hand. Let's see if we can do one more quick demonstration just so I can show you that infrared light here, this thermal infrared light, that is allowing us to see things that have a higher temperature. Or actually, everything is giving off infrared light, or everything you and I are, everything at about room temperature. And we could see that even if I could turn off all of these lights. Let me go ahead and plunk my hand down. As you can see, my hand is pretty warm right here. And this camera, what it's doing is it's blending in some visible light. That's why you can see the details as a visible detector and an infrared detector. So you can see the thermal infrared glow with the temperature bar on the screen. But what I'm doing is I'm putting my hand on this table. I'm warming up the table, and I can pull my hand away and you can still see my handprint right there on the table. You even see the thumbprint. So what am I doing with all of this? I am just showing you that everything that has a temperature gives off light. Things that are the temperatures of like you and I, the kind of temperatures we experience on Earth, we're giving off lots of infrared light. We just can't see that with the human eye. But if we were creatures that could see in the infrared at these wavelengths at about 10 microns or so, 10 micrometers, then even at night, our world would be shining brightly. Okay, so if we're going to talk about thermal radiation, we have to talk about temperature. And let me go ahead and bring up my slides for this. Just wanted to go ahead and show you that things that are around you are warm, and that things that are warm, things that have a temperature, anything that has a temperature gives off thermal radiation. Things that have temperatures like you and I at about 300 Kelvin or so, we give off mostly infrared light. So again, if we had infrared eyes, we would all be glowing. Here is what my workstation looked like while I was putting together this video in the infrared. So you can see my computer was working pretty hard, and this bright part right here means that, hey, that's where it's warmest. You can see my little connector to my second monitor is getting hot as well as it heats up as it's working. And then here's a picture of my face. You can see that I got some seriously cool eyebrows going on there. Okay, so thermal radiation. And the key to what we're about to talk about, because what we're trying to do is we're trying to connect a fundamental thing, temperature, understand what temperature is, and relate that to how dense objects are giving off light, how I am emitting electromagnetic radiation right now, mostly in the infrared, how the sun is emitting mostly visible light. All of those are examples of thermal radiation, how hot, dense objects emit light. Now let's drop the hot part, how dense objects emit light. Hot, dense objects are hot enough to emit visible light. Okay, so all dense objects emit light. The type of light that they emit is called thermal radiation. So what was being detected by my thermal infrared camera was this infrared light given off by an object that has a temperature. Let's talk about a couple of things. What do I mean by dense? So the qualification of what dense is in astronomy, there is actually a definition of it, but it's beyond the scope of this course. It's a little bit complicated. But let's just go with a list of things that are dense enough to give off thermal radiation. You are dense enough to give off thermal radiation. I am dense enough to give off thermal radiation. The water in my water bottle is dense enough to give off thermal radiation. This juggling ball is dense enough to give off thermal radiation. The water in a pool is dense enough to give off thermal radiation. Pretty much every solid and liquid is dense enough to be emitting light as thermal radiation. Most gases are dense enough, so stars are dense enough to give off light as thermal radiation. So planets themselves, a solid object, is dense enough to give off thermal radiation. Jupiter, a gas giant planet, is dense enough to be giving off thermal radiation. So if we're going to be studying the light that all of those objects, stars and planets, are giving off, we will be studying their thermal radiation. So we want to understand it. How those dense objects are going to be emitting light, how that thermal radiation is given off, all of that is determined by only one thing. You only have to worry about one thing if you're talking about thermal radiation, and that is the object's temperature. The temperature tells you everything that you need to know. How dense objects emit light is determined solely by their temperature. And I just want to go ahead and, since people might not be familiar, but it's a term that we're going to be saying a lot. Here, whenever we say emitted light, we mean that something is giving off light. It is emitting light. It is glowing at those wavelengths. And what do I mean by how it is giving light? Well, the things that we're really going to be after is we want to know how bright something is. So how much light in total is it giving off? And then we want to know how bright at each wavelength. So we can see down here with this lava that's flowing, this nice little lava river, that some of it appears to be yellow and almost white up here. So, and some of it is sort of a deep red, some of it is an orangey color. Clearly, it's giving off different wavelengths of light, different wavelengths of visible light, and a different balance of how many of each type of visible light is giving off. Each wavelength of visible light is giving off. So we want to know how bright in total it's giving off. So how many watts is that light bulb is really the answer to that. How many watts is the light bulb of the sun? How many watts is the light bulb of that star over there? How many watts is the light bulb of that really cool exoplanet I want to know more about? We want to know how bright overall something is, but we also want to know how bright at each wavelength. Is that object giving off more visible light than it is giving off infrared light? And as I was heating up the coil on my stove, you saw that something, as it got hotter, while it was still cold, it didn't give off any visible light of its own. It was reflecting light, but it wasn't emitting its own visible light. But then as it got hotter, it started to give off visible light. So clearly, what wavelengths of light an object is emitting depends on its temperature, such that as the temperature gets hotter, it likes to give off shorter wavelengths of light. So for all of this, we really need to understand what we mean by temperature. So that's what the majority of the rest of this video is about, is what is temperature. But we have this cool little GIF of, yes, it is GIF of lava over here. So let's just talk a minute about this picture. So lava is hot. That's a pretty inane statement. We're all pretty aware that lava is hot. But lava is also dense, which means that it's giving off thermal radiation. So here we have an example of thermal radiation. We see that some of it is glowing red hot, some of it is sort of glowing yellow hot. The yellow hot part is hotter. The hotter you get, the more shorter wavelengths you give off. And if you remember from our previous video, that yellow wavelengths are shorter wavelengths than red wavelengths. Red wavelengths are the longest wavelengths in the visible spectrum. So this region right here is hotter than this region over here. So it's emitting light, is emitting visible light wavelengths, but it's also emitting a lot of infrared wavelengths. If I were to shine my camera that can detect infrared wavelengths, look at infrared wavelengths at this, the entire chip would be flooded. It'd be so bright that we couldn't see any detail, because it's going to be really, 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 really bright in the infrared. And that's why you can feel it whenever you get close. Our body interacts with infrared radiation very, very easily. So you'd feel that as heat coming off of it. And this region that's brighter is going to be hotter than this region that's dimmer over here. So total brightness is connected to the temperature. The hotter it is, the brighter is going to be. But what about the surrounding rock? Clearly not giving off its own visible light, but it has a temperature and it is dense. Is it giving off light? Absolutely. But we would need, it's giving off infrared light. It's cold enough where it's not giving off any visible light. It'd have to get hotter, like that lava, that molten rock, to give off visible light. Okay. So what do we really mean when we say temperature? Here I am sitting in this room, and I feel a temperature. It's a little cool right now. Thank you, fall weather. Also, happy fall equinox if you missed it this week. It's cooler weather, and I can feel like, yeah, it's a little bit chilly in here. We feel, we sense, we perceive temperature, but what is it that we're really sensing? What is temperature? Rather than some number we read off a thermometer. How does that number get onto the thermometer? What is actually going on with the air in this room that defines its temperature? What's going on with the particles in this table that define its temperature? And here we're actually going to get at the true definition of what temperature is, or I should say one, maybe not the true. It's always a dangerous thing to say. One of the definitions of what temperature is, the physics definition of temperature, or one of the physics definitions of temperature. So temperature is really just a measure of the microscopic motion of the particles of whatever you're trying to measure the temperature of. So all the air particles in here, they're not just sitting still. It's like this box that I have over here. This is gas particles in a box. They're always moving around, bouncing off one another, bouncing off the walls, bouncing off this table. They're always moving around. Some of them are moving really fast, some of them are moving a little bit slow. On average, you can define an average speed, and it's that average speed that all the air particles are moving at. That's what defines the temperature. So we define temperature by the average microscopic motion of the particles of something. We could take a solid or a liquid. So if we could zoom in onto the molecules and atoms that make up this table, we would see that they're not sitting still. They're jittering back and forth. That's what this image over here is trying to show you. They're jostling back and forth a little. And the speed that they're jostling, their average microscopic motion, if the table is hot, they're going to be jostling around really, really, really fast. The table is cold, they're going to be just barely and slowly jostling around. So higher average motion, higher temperature. Lower average motion, lower temperature. And that's really what we're talking about when we're talking about temperature. We just perceive and we feel that because of the nerves in our skin that are able to detect that sort of a thing. So basically, we are equipped to detect average motion of the air particles in this room. If all of a sudden I feel warmer, I'm really detecting that the air particles in this room are moving faster. Weird to think about it that way. If I jump into a freezer, I'm like, dang, I'm cold. The air particles in here must be moving really slowly. This is just for the curious. That's why I've marked it in green. This is what's called the Maxwell-Boltzmann distribution of velocities for, say, gas particles in the air in this room. And what it's showing you is the probability of a gas particle traveling at a given speed. So faster speeds and probability of this curve. So it's showing you just what the speed distribution of particles are. Go ahead and think about, like, memorize what this shape is a little bit, or just burn it into your brain a little bit, because that shape is going to become a familiar looking shape very, very soon in a video coming to you very, very shortly. Not this video, but the next video. And we can see that some particles are moving really fast, some are moving slow, and we can define an average speed. And that average speed determines what temperature is. Okay, so temperature is absolutely important. What kind of temperatures do we talk about? I talk about the temperature in this room. It's like 67 degrees Fahrenheit in here. It's about, let's see here, what is it? It's about 20 degrees Celsius in here. That's how we usually talk about temperature throughout the entire world. We use degrees Fahrenheit or degrees Celsius. The US is weird, and we're pretty much the only ones that use the Fahrenheit scale anymore. But all of those are temperature scales that are defined relative to something else. I'm not quite sure what the Fahrenheit temperature scale is based off of. It's a little bit weird. The Celsius temperature scale is based off the freezing point and boiling point of water. We define 0 degrees Celsius as the freezing point of water and 100 degrees Celsius as the boiling point of water. And then we extrapolate to either colder or hotter from there. For Fahrenheit, freezing is 32 degrees Fahrenheit, freezing point of water, and boiling point of water is 212 degrees Fahrenheit. These are defined by water. What we want, if we're going to actually do the astrophysics of this, if we're going to understand how these physical phenomena are operating that are related to temperature, like thermal radiation. So how is thermal radiation related to temperature? We want to use a temperature scale that's actually derived by the definition of temperature itself, that's based off the thermal motion, the average thermal motion of particles. For us in astronomy, that temperature scale is called the Kelvin Temperature Scale, named after Lord Kelvin. He was the Lord of Kelvin. So that was not his real name. He was just known as the Lord of Kelvin. So the Kelvin Temperature Scale is actually based off the thermal motions of things. And in fact, we set the 0 point of the Kelvin Temperature Scale. So you can imagine if I got the air in this room to be colder and colder, the average motion would get slower and slower and slower and slower. And let's go all the way to the logical extreme here. We could theoretically get the air so cold in this room that all microscopic motion would stop. So cold that there is no motion. Let's define that as our 0 point of a temperature scale based on the average motion of particles. That is what we call absolute zero. And for the Kelvin scale, that is 0 Kelvin. It is a theoretical limit. We can't actually make anything. Our understanding of quantum mechanics, the theory of quantum mechanics, says that there will always be some motion. So it's impossible to reach 0 Kelvin, but we've come really, 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 really close to 0 Kelvin, absolute zero in a lab, and really strange things start happening. I encourage you to look that up. But 0 Kelvin is defined as when all the microscopic motion would stop. So we have our 0 point based on thermal motion. And now we can just set a difference of 1 Kelvin to be the same thing as the difference of 1 degree Celsius. So we piggyback onto the Celsius system. So in the Celsius system, we would see that absolute zero is minus 273.15 Kelvin. And that allows us to build our entire Kelvin scale. We go from 0, and then by the time we hit 273.15 Kelvin, we're at the freezing point of water, 0 degrees Celsius. And then we'd have the boiling point of water to be 373.15 degrees Celsius, or 373.15 Kelvin. And if you want to know just a sort of waypoint, 300 Kelvin is a good number to stick in your head. It's about 80 degrees Fahrenheit. So a little bit warmer than normal room temperature. A summer's day is about 300 Kelvin. Notice that we're not using degrees Kelvin because this is an absolute scale, not a relative scale. Okay, I know that was a very long video about temperature, but I hope you got to appreciate a little bit more about this physical world that we live in. I'm spending more time on temperature than I ever have before because it is the actual physical thing that we need to understand. We need to know what temperature is. So then we can exploit how objects that have temperature give off light. Because if we understand that, then we can look at the light that something is giving off, say the sun, or that star in the sky, see how much of each wavelength of light it's giving off, and use that information to determine the object's temperature. We are developing a thermometer for the universe. All right, we'll continue that development of a thermometer for the universe in the next video. Thank you for tuning in.